So I'm going to do an example of balancing using the oxidation number method with a tricky redox reaction that balancing by inspection may have been difficult. So one thing you need to do right away is, I'm going to change this. So I'm going to do an example. Of balancing a redox reaction using the oxidation number method. This was the example I gave in the last video, and it was kind of tricky. And maybe you tried balancing it just by inspection. Probably did something like, okay, we definitely need a 2 here to balance out the 2 potassium on the reactant side. And then there are so many different places where sulfur, hydrogen, and oxygen came up that trial and error could have got you the correct answer eventually. Using the oxidation number method will be a lot easier. So the first step in doing that is to write the oxidation numbers of each element. So here we have potassium permanganate, so oxygen is -2 and potassium is +1. This manganese would then have to be +7 because it's a neutral compound. 4 times -2 is 8. The +1 would mean -7, and the +7 would have to balance it out. Here you have hydrogen being +1 and sulfur being -2, balancing themselves out. Oxygen -2, hydrogen +1. Sulfur in this case is going to be +6 because you know sulfate has a -2 charge. 8 electrons from, I said 8 again, 8 oxidation number from the oxygen here, -2 times 4 giving -8, and then the 2 hydrogens will be the +2 that balances out your -2 charge from sulfur. You have sulfur existing here in dihydrogen monosulfide and in sulfuric acid with 2 different oxidation numbers, and that may be one of the reasons why this question is tricky. Potassium is still +1 here, and your sulfate remains +6 for sulfur and -2 for oxygen. Here, sulfate again +6 and -2, but manganese will be +2. So this is our first example where our oxidation number for an element has changed. We link those right away. Sulfur in its elemental form is just 0 here, and then water, oxygen -2, hydrogen +1. So hydrogen and oxygen don't change at all throughout this question. And the sulfur in the sulfates will remain +6, and then this sulfur will be where the other redox reaction occurs. So going from +7 to +2 means you have gained 5 electrons, and going from -2 to 0 means you have lost 2 electrons. So the losing of electrons is oxidation, and the gaining of electrons is reduction. We now have our oxidation and reduction half reactions locked in. This will have to be ×2, and this will have to be ×5 to make 10 electrons reduced and 10 electrons oxidized. Here, the 2 will appear in front of the coefficient that we already wrote in for inspection, and will also have to appear here so that our manganese is also balanced. And then the 5s we can put in front of these elements, meaning 4 of the compounds or elements in our reaction are locked into this ratio. 2 to 5, and these have to be a 1 to 1 or 5 to 5, and these have to be 2 to 2. All of those can't change. If you have to multiply, say, this sulfur by 2, all 4 of these compounds have to be multiplied by 2 to keep your electrons balanced. Now, we can look at this equation and balance the rest of the elements by inspection. Here you have 5 sulfurs and 1 sulfur here, and then you're going to have 2 sulfurs and 5 there. And 1 there. May not be the best one to start balancing next. You could look at the hydrogens. Here you have 5 times 2, and here you have hydrogen, and here is where all your hydrogens are going to go. And then you're going to probably want to do oxygen next. So I will start with sulfur. 1, 2, 3, plus 5 is 8. 5 here, I'm going to put a 3 in front of sulfuric acid so that sulfur is balanced. Hydrogen, now, we have all of these balanced on this side. All of these here and these 2 compounds of hydrogen on this side. 10 plus 6 is 16, meaning 8 waters will need to be produced. And then we got to check our oxygens. Here you have 8 plus 12, so 20 total as a reactant. 4 plus 8 is 12, plus 8 is 20, 20 as our product. And that is our final balanced chemical equation using the oxidation number method.